And hopefully I can share my screen. Okay, sorry, I'm just gonna load the whiteboard now. Okay, and this is gonna be the classic thing. So, Jason, I'm gonna make it your job. I'm gonna share my screen, and hopefully it'll share okay. But whenever on the screen, if it's sort of going off the edges, do you mind just letting me know? You guys have Julian Epps for 2134, and go off the PowerPoint. So I'll make that your job. Nicola, can you see my screen at the moment? Is it sharing?
Yep.
Cool. So, okay, great. Okay, finally we can start. So sorry for the delay, everyone. Welcome to the crash course. Hopefully we'll whiz through this first little bit so we can get started. Okay, 3, 1, and 4. Okay, participants, great. Okay, great. Nothing recordings. Okay, so crash course. I'm going to set the background. 2 dots. Perfect. Okay. I feel good. Okay. So first, 3144. What a great course. Okay. So I hope we're all loving it so far. So since the midterm, I'm going to assume we're going to cover all the stuff from there. So Jaden, what sort of topics have we covered since the midterm exam?
State feedback. What else did we do? PID design and stuff like that.
Yeah.
I know we just started on Root Locus on Friday. Yeah, I think that was mainly it from stability, maybe. I don't know if we've done that for the midterm or not.
I think, yeah. Errors, steady state, that sort of stability things. Great. And then 2 of the things we won't cover, and I'm pretty sure we can go through this if you do want to. I've revised on it. It's frequency response. I just don't think you've covered that in lectures yet if you've just gone on to Root Locus. Is that correct? Kurt, do you know, have you covered frequency response like Bode plots, Nyquist plots, those sort of things yet? Or Taban, do you know? Yeah, no, that's okay.
I beg your pardon.
Yeah. Are you up to date on lectures? Do you know if you've covered frequency response yet? So things like margin, gain margin, Nyquist plots.
I have no idea about that actually. I'm doing a supplementary this year. I did the whole course last year, so you know.
Okay.
Yeah.
Okay. Thanks, Andrew. So we haven't yet. Okay.
Yeah.
So I'm gonna do a little bit of that at the end, depending if you have time, and then also just to start off, just to bring us back to speed. This might seem like we're recovering content, but it's really important. We'll just re-go over before we jump into PID design why we're doing it. So a bit of a recap on pole placement techniques. Okay. Okay, great. And then so during this, what we'll do is we'll do a section, and then hopefully we'll follow that up with a bit of a past paper to get a bit of practical, experience in it. But mainly, yeah, we're trying to focus on the high level little tips and tricks, and also because in the lectures they go quite in depth, and some of the stuff you don't really need to know. And if you look at through some of the past papers, as I hope you're doing it now, I won't choose these past questions. So have a look through, because what I will do actually is I'll share a screenshot. And what I've done is I've broken down each of the questions into what they cover. So have a look through some of the past papers, look through the question as I'm sort of getting set up here. And yeah, either write in the chat or turn your mic on when we get up to those points. And we'll look through those. Engage file. Okay, great. I'll just send that screenshot. Yeah, Meng, did you get that? Yeah, perfect. Awesome. Great. Okay. So first thing we'll start off with. So is it Yuji Shen? If you can turn your mic on and say hi. Okay, we'll go to Nicola. So for our overall control system, how do we usually draw that in block diagram? Nicola, Jian, then? Do you have any idea how we draw a block diagram? Oh, okay. Okay, that's really hard.
If you stop sharing video, it might make the audio faster, maybe. I don't know. Just something to try, possibly.
Yeah, that's a really good point. Okay, great. But that's also going to stop the recording. Actually, what I might do, is anybody willing to share their screen to share their version of the whiteboard just to watch?
Yeah, I can if you want me to.
Yeah, great. That would be awesome.
How's that? Fine?
Okay, great. So how's my audio quality now? I might have just probably maxed out my my internet speed.
It's sounding better.
Okay, great. So no sort of lag.
Not as much as before, maybe a tiny fraction, but it's 10 times better than it was before.
Yeah, great. Okay, I'm just going to switch over to mobile and see if that helps us. Okay, this is a test of the audio quality now. Is that better? Can anyone hear me? And is
Yeah, I
this
think it's about the
audio?
same. Yeah.
Was this better than last time or the same?
Seems less laggy.
Cool. Okay, we'll go with this then. Cool. Okay, and yeah, hopefully it doesn't lag too much because lag is a big problem. So Jeremy, if you can hear me, how do we go about drawing our control system?
Block diagram form. I'm not sure.
Yep. Okay. So first we start with our plant. So this is a block diagram. We have G, and then our output is also Y of T, and we know we've got some sort of controller GC. We have the input. What do we call the input, Jeremy?
So is that just the error
Perfect.
signal?
And then we have the error.
Yeah.
Okay, and usually we call in between the control. And then we have negative feedback denoted by this negative sign. Okay, so this is all very stock standard. Hopefully we'll whip through this. So for our PID controller, Jason, with our PID controller, how do we usually write that in our transfer function?
As in for like the closed loop system?
For the open loop, so just for GC. In terms of, KP, KI, etc.
Oh, it's KP plus KI on S plus KD times S.
Yeah, great. And then do you know, in terms of integration or differentiation, what those multiplications or divisions are doing?
KI gets rid of the steady state error.
Perfect, great.
KD had something to do with like overshoot settling time. I forget which one though.
Yeah, great. So what we'll do is here we'll draw a generic. So we'll say this dotted line. So that's going to be our reference, R of T. Okay. And then our Y of T output is going to go up. It's going to have some overshoot. And for people who are in the last the last crash course, we know that there's this sort of exponential function. Okay, and I'll draw over on the right-hand side what we mean by that. So if this is a pole here, okay, the X and the Y intercept, Jaden, do we know what those are? Looking at the characteristic equation.
The Y-intercept is what, omega D, and X is sigma. I forget
Sigma
what.
D, perfect. Yeah. And then what are the two other factors that relate where the poles are? The two
omega N.
Yeah.
And there was one other thing, zeta, which is the angle, isn't it?
Great. Yeah. So zeta is cos theta. Yeah. Okay, with theta being the angle. So it's two things. So either, and this is the S plane. Okay. So we can say and I always draw a characteristic equation. I draw that as lambda S. Don't ask me why, but it'll be that there's two ways of drawing that, right? So we can either say it's going to be S squared plus 2 zeta omega n S plus omega n squared, stock standard, okay? But a slightly different way of writing it would be S squared plus 2 phi d S plus omega d squared plus phi d squared, okay? And that term there on the right comes from the fact that if you look at this this image down the bottom, you can see just using Pythagoras' theorem that omega n, which is the radius of the vector which leads to our pole, that squared is just the x and the y squared. So that's where that comes from. Okay, so these are the two denominators of our closed loop transfer function, and they'll get this pole, but from these locations, as we said before. So we know that the transient response, so this is a function of time, we know it's going to be bounded by this e to the negative phi dt. Okay, so that's going to affect things like the overshoot, and we know that it's going to have a frequency of cos omega dt. Okay, so that's going to affect things like the rise time and the settling time, etc. Does that make sense? Okay, so Gina, are you there? No. Eric, can you hear me?
Yep.
Yeah, okay, so Eric, looking at this transient response, what do you think is the major thing, either the proportional, integral, or differential? What do you think the proportional part, KP, what is that going to affect the most in terms of our transient response?
Well, I think that's just going to be like the first initial jump up, right? That's going to be causing the transient to move up the fastest.
Perfect,
initially.
Great.
And then
what's KP also related to?
The error signal? I don't know.
Perfect. Yeah. So usually it's roughly inversely proportional to the error. Great. And then keep going. So KD, what part of the signal do you think that's going to be related to?
Right. So I think KD is it's a derivative, right, of how fast it's increasing as compared to the error signal.
Perfect.
So
yeah.
When it I guess when it crosses the error the reference signal for a step, that's probably when it's the highest.
Mm-hmm.
I think.
Okay,
Yeah.
so when it's moving the fastest.
Yeah.
Okay, so do you think that's having an integral or a differential relationship with x of t?
I'm gonna say differential.
Yeah, great. Okay, so what I'm going to do is up here, I'll just write d on dx. Okay, so it almost that s acts as a differentiator, and if you look at your Laplace transform rules, you'll find that the Laplace transform of the derivative is s. So it's hard to sort of get your head around because we're always taught the s plane, etc. This is a good way of remembering that, and then finishes off there. So ki, what does that affect?
That's just the integral between that difference, in that error signal, and the actual.
Okay. So that means the steady state error usually goes to 0 at that point, because we have that 1 on S term. Okay. So the second thing that we go through, and so I'll draw this down below now. And the first thing we sort of start off when we're looking at root locus is we're given three different demands. Kurt, can you take us through some of those three? Kurt, are you there? Great. Okay, maybe not now. Yeah. Okay. No, that's so fine. Don't worry. This is an overview, so please don't worry if you haven't caught up to lectures, etc., etc. It isn't a waste of time being here. It's good because this will give you a really good overview before you start studying now in these final weeks coming to exams. So it's still a really good way to spend time. Let's go, maybe Jason, can you answer that one? So the three sort of time characteristics we usually place under our control system when we're trying to design a system.
You talking about settling time, peak time,
yeah.
rise
Perfect.
time?
Yeah. Okay, and do you know how, the formulations of those? And we get a formula sheet, which is great, but can you remember any of them on the top of your head?
Overshoot is negative ln Oh wait, that's
Yes.
that's zeta. It's e to the power of what was it?
That's overshoot, I'm pretty sure.
Yeah,
So-
pi squared.
Zeta omega n.
Awesome. Yeah. Okay. And another way we can write this, we went through this last crash course, but we can also write that as negative phi d on omega n. Okay. And what we're going to do now is we're going to start having a look at how they're getting related. Okay. Because what we do is there's three major steps. So we get these three functions, and then from those we can work out what phi d are. And then what we do is we take in, I'm going to cut and paste these relationships up here. We take those in until we can get two of our desired poles. Okay, and then what we can do is we can use pole placement. So using our PI or PD, we can actually make it so our closed loop poles come to be exactly these, which have exactly those characteristics. Okay, so I think TP was just pi on omega d, TS was 4 on phi d. As a note, phi d is just 1 on tau, so it's just 1 on the tau, sense because it's part of it. And I'll just write out the equivalents over here. It doesn't matter, you don't need to remember these, but it's good to have in mind because we'll look through now how they relate to each other. Okay, so here we see that TP is sort of related to omega d, okay, and we know that that's going to be related somehow to KP and KD, right? Because they affect, you know, whether it's rising or falling. And I don't have, I think we'll draw out a little table maybe to the left just here. So we'll have KP, KI, KD, okay? And who else do we have here? So Taban, do you mind? And also, if I'm missing anyone, please yell out. I'm just trying to go through names and I'm writing down people who can have mics. But Taban, do you know what happens? So to the percent of overshoot, as we increase, you know, KP, KI, or KD, just looking at this graph, can you have any idea of how they would be affected?
I believe if you increase KP or something, there'll be like under damping or something more, perhaps.
Yeah, so there'll be more overshoot. Great. What's going to happen to our settling time?
Settling time will go down a bit. Yeah.
Yeah. So if we look at omega d, okay, so we know it's related to that phi. Our KP actually doesn't really do a lot in terms of settling time because that's more related to omega d. So there's no real effect. But what about the steady state error? So as we give, you know, more gain to our system, does that error increase or decrease or stay the same?
I think it stays. Let me have a look at that.
Yeah. So it decreases, I think, for first order systems. For higher orders, it's a bit hard to say, but usually we say that decreases. And as we said before, with integral design, error steady state goes to 0. And if we're damping it, it doesn't really have any effect, right? But what does damping have an effect on? Taban, do you want to continue on for that? You know, in terms of overshoot or settling time, what's the effect of damping those oscillations going to have on both of those?
I think the error, like, you know, the error on the whole thing, how much time it takes time to settle, perhaps.
Yeah, so the settling time is going to go down. What about the overshoot?
Overshoot, damping. I don't think it will have an effect on that.
We're damping those oscillations down.
There'll be more overshoot.
So the more overshoot, because we're doing that derivative gain.
Yeah, more overshoot.
Yeah, okay. Okay, but if we think about it, right, because what we're doing is we're taking the derivative. So the faster it's increasing, derivative gain is going to act against that because we're damping that. Okay, so So
if we go-
KD is actually going to be damping those oscillations. So it's going to decrease the overshoot because we're slowing down those oscillations. And then just to finish it off, so KI, usually because it has a small effect on increasing overshoot, the main two effects is making the steady state error go to 0, and it also increases the settling time. And the way to think about that is that because we're taking this integral, its effect is going to die out a lot longer, if that makes sense. Because what it's taken is the integral of the error, and of course that takes time to go to 0, but eventually it will go to 0. So that's good just to keep in mind how you increase or decrease those, not necessarily in an exam, but they might ask you, how would you tune your results once you get them? Okay, so coming back to the 3 sort of steps of pole placement. So this is step number 1. We get the overshoot or peak time or settling time, and then we work out for what either phi or zeta are. The second thing is we look at this, we look at the characteristic equation, and the third thing that we do is we equate that characterization, to our closed loop response. So this is T of S, which is, I think it's GCG on 1 plus GCG, okay? And just so we don't have to memorize a long thing, I'm going to spit out, the full formula, and we'll work at how it simplifies. Okay, so we've just got KDS plus KP plus KI on S. Okay, and what we're going to do is to get it out of that form, we times everything by S, so the top and the bottom, which means it's going to increase the order. Okay, so we're going to have an S cubed term. And that's why we normally don't do full PID designs when we're designing it. Usually we just do PD, and then we add a little bit of PI if we want that steady state error to go to 0. But I'll touch on this again when we look at, I'm pretty sure, Meng, are you there? Have you covered lead lag compensators yet? Okay, I don't think you have at the moment covered lead lag, so I'll give a brief overview of that. But lead lag is just if you get a response, how can we speed it up or slow it down by adding extra poles and zeros? And I'll get into a little bit of how that works. Okay, so it's S cubed plus, in here we have A1 plus KD. Yeah, don't worry, Yamang, it's fine. I think we all are a bit behind. A0 plus KP. And then plus KI. And if you're wondering where those A0, A1, etc. are coming in, this is assuming we have a second order G. So our G, our plant is K, some sort of variable gain, plus S squared plus A1S plus A0. Okay, so all I've done is just done the maths, combining, I'll just let's see this a little bit. Okay, so I've just combined these two formulas, so G and GC, combine them together into our TS, and this is what it comes out to. But what we'll look through now is just how it relates to PI and PD. Okay, because usually pole placement, as you can see from this above equation over here, our characteristic equation only really relies on having 2 poles or 2 dominant poles. Okay, so we have to kind of simplify this third order response to a second order. And there's 2 ways of doing this. So what we do is we either have
add that transfer function, sorry. The TS, shouldn't it be A0 plus KP times S?
Yeah. So at the bottom, denominator A0 plus KKP into S for the TS formula. Yeah.
Yeah. Perfect. Great. Thanks for pointing that out. Yeah. So there is an S there. Thank you. And then plus KI. Great. Okay. So the first thing we can do is we can look at, okay, so for a PD controller, okay, and if there's one thing I want to take out of this this crash course is PD. So this derivative control, usually it's the main thing we do if we want to get a specific transient response. So we can usually get it via integral response, but usually we go through PD. And the reason why I'm saying that is it will come in a little bit later on, but just keep that in the back of your mind. So for a PD, if we have a second order system, we know that Ki will be set to 0. Okay, so just looking at the above formula, we can just rewrite it. So we have Kd s squared plus Kps over s cubed plus A1 plus Kd s squared, okay, plus A0 plus Kps plus Ki, okay? And what's going to happen by setting Ki to 0, so sorry, this will also go to 0. I'll just erase this so we can see a little bit better. So that was plus Ki. Okay, so that'll go to 0. So, and what we can do is we actually can cancel a common factor of s out, since we can cancel this s from the top. So I'll just write this in red. Cancel this s. Okay, and that leaves us with the common formula we have when it comes to PD controllers. Okay, all we have to do then is just match these two forms. So the S matches with the S term, and then the second form also matches over here. Okay, and this links back, I'm going to draw a big green line. So these two relations link back to what we were talking about before. Okay, and sorry if it was a bit confusing when I was just telling people like, oh yeah, like this is related, this isn't related. So let's pick an example. So if we look at the characteristic equation, so s squared plus 2 phi ds, okay, so this term here in the characteristic equation. So we know that phi d, it affects the exponential. So that exponential curve that's damping the response. And we know that phi d is also related to K and Kp. Okay. So K and Kd, and is it up here, D? Is it D? I'll just rewrite that. K, Kd. Okay, so they're proportional to each other. So, you know, as we decrease Kd, that's going to also, I think, decrease phi. Okay, and as we decrease phi, that exponential is going to tighten. Okay, so it's good to have a look through those relations to see how they affect each other, because we can kind of reason it in the time domain in terms of the damping or the proportional, but it's good to also see it in the maths of how they're related. Okay, and I'll quickly just go through the PI. So with the PI, what we do is we set KD to equal 0, and also what we do, and this is why PI, we don't really use heaps for these sort of questions, is we say we only use G equals K on S plus A1. Okay, so we reduce the order of our controller by 1. And essentially, if we go through the maths again, so we have K, we have KD S squared plus KPS. Does anyone have any questions so far from the end of this section? And if you have any questions as we go through, feel free to turn the mic on in the chat, etc. And if you're feeling lost, that's completely fine. We all feel that at points. So here, so KD, we set to 0. Okay. And what happens is, because we're only using a first order system, this S cubed also gets reduced. Oh, I just realized I have written those the wrong way because my P's look like D's. So this is A1 plus K, K, P. I'm pretty, oh, no, it's KD anyway. Getting my P's and D's confused, but it's not important. So it's actually here. So this part goes to, we'll skip this part. My whiteboard isn't responding anymore. Okay. Okay, so that's our little recap on poll placement. Okay, so that's the perfect ideal response. So what we want to do is we look at the overshoot, the peak time, the settling time. Okay, going back, so we have this first step here, and then from there we get those characteristics. So either zeta and omega n, or we look at phi d and omega d. Okay, and from that we get the characteristic equation that we want, and then what we do is we equate that to the characteristic response of our closed loop transfer function T of S. And then from that, hopefully by equating those two equations, we can get, because usually we have two unknowns. So we have, either zeta and omega n, and we have Kp and Ki or Kd. And then from those, we can get the proportional or integral parts. Okay, but sometimes that doesn't work. Sometimes we can't solve those equations because we don't have, enough knowledge. So that leads us to the second thing, which is root locus and PID design. Okay. So I'm going to start a new section. Just get rid of this so we can fit it all on the same page. I'm going to write it over here to the right. Whoever's on the sheet, I'm not sure if it's just following along, but I'll be writing a new page over to the right of here now. Okay, so how have we gone so far? So Nicola, what's making sense and what's not making sense?
All good at the moment, I think.
All good at the moment, okay. What's one thing that didn't make sense from the last little bit, or what's the haziest part of those three steps that we just covered?
Probably the third part, but
yeah, that last part, which is great because I did screw up the maths I think a little bit there. So that's where it comes to. So this is the generic formula down here, which I've written out, but usually I'm doing that hopefully just to build some connections for you. But what you would do is you'd use this, which I've circled in red over here, because your controller will change, okay? And we know that from there we can get our characteristic equation, which is on the bottom, okay? And we can equate the two, and that will hopefully give us the two sets of equations that we can sort out. So building on from that, so here we've got, I've written up on the right-hand side, transfer function T, so K, GCG, and what we know that the bottom is our characteristic equation, so we know that 5S is 1 plus K GCG, okay, and we know that that's equal to 0. So what we can do, and this is the basis of root locus, I'm sure you've come up to this, but we can write K GCG is equal to -1. Again, another way of writing that is that the magnitude of K GCG and the phase of K GCG is equal to the magnitude of 1, which is just 1, and the phase of 1, which is 180 degrees. Okay, but it's not just 180 degrees, it can be any multiple. So usually put a 2K plus 1 in there. Okay, so that's essentially the basis for our root locus desired. Okay, and the reason where that comes from, why this -1 is important, Taban, do you have any idea of why in control systems, that -1 is an important point.
I'm assuming it's because it's more stable on the left-hand side and it's unstable on the right-hand side.
Great, okay, so if we look at the Bode plot here, we're always told, okay, we've got to keep everything on the left-hand side. But where does that come from, okay? This is something I always used to ask myself. So it's come from this equation here, because we know that T, if this denominator here, if KGCG equals -1, T will be, something on 1 plus -1, so it'll be something over 0. So T will go to infinity. And we know that T is just our name for the overall transfer function, okay? So T is our closed loop. So it's as if we had R, so it's as if we had R going into T and outputs Y. Okay, so if T goes to infinity, it means that for any R we put in, Y will be infinity. Okay, and that's classically what we call unstable. So that means for any starting point you have, okay, it's always going to oscillate to infinity. Okay, and if you had anything under infinity, so let's say our transfer function T was like 1,000,000 or 1,000,000,000, that's not going to be unstable, right? It'll be amplified by 1,000,000, okay? But that won't be infinity. So it's the classic, to get infinity, you've got to multiply by infinity, okay? So that's why that -1 is so important. But why does that come to the left-hand plane? How do we get there? Jaden, do you have any idea why that -1 corresponds to the left-hand plane, where that came from?
I just know where it comes from when you derive it, but intuitively, no.
Okay, so this comes back to maths, and honestly, I don't remember a lot from maths, but there's some really great there's a reason why we did second year maths, okay? And I think some of you would remember, and maybe not with fond memories, but when I say things like a contour plot or residues, okay, so we were looking at, residues, roots, complex things, and contours, from 0 to infinity. But all we were doing, and what that was preparing us for, was S-planes, okay? So we know that on the omega axis, omega goes from 0 to infinity, okay? And that's the same, and you'll come across this in Nyquist plots. Okay, so essentially in a Nyquist plot, everything's sort of circular. And what happens is when we go from the Nyquist to, not the Bode plot, sorry, that's the wrong thing, to the S-plane. Okay, what we're doing is we're doing a mapping, okay, from, it's like, what do you call it, polar coordinates to, rectangular coordinates. And hopefully you remember at some point, it was almost like this unwrapping of the circle, okay? And that circle unwraps, and that circle passes through, I should redraw that, because actually that circle passes through -1. Okay, and that's a very important circle. And that maps to the J omega axis. And what we want is we want all of these poles to be within that circle or to the left-hand side. Okay, so don't worry, if this all goes over your head, that's completely fine. It has no real relevance, but it does tie together S-plane and Nyquist plots quite nicely when you do get up to them at the end of this week, etc. And it does explain why that -1 point, it links this equation here, so this maths, okay, with this more graphical approach. Why that -1 point is important. Okay, and this forms the basis of all our root locus, because all we're trying to do is to find that point, which is defined as the root locus, where KGCG is equal to -1. Okay, and through that, because we're working with complex things, it's almost like we always get two equations for one. So we get this relations here, so KGC of G is equal to 1, and we know that the angle is equal to 180. Okay, and that gives us this map. So if I have, this is a classic, I won't go through sketching root locus. I'm sure you go through it enough this week. What I'll do is I'll just basically go through the two main rules. So rule number 1, I think they usually list like 8 or 9 rules, but Actually, Jason, have you been through Root Locus? Do you have any idea of the rules of Root Locus? Has Arash covered that yet?
I think we've just done it.
In lectures, cool.
Lectures.
So it's basically saying, we start from, I can't remember, it's closed loop or open loop as the poles, but essentially what it's saying is as we increase the gain of our system, how do those poles move? Okay. So the first rule, so we draw these lines, okay, and we call this the root locus. And it means that for any gain, so when gain equals 0, they start at these points. So I'll draw in red. So this might be k equals 1, okay, and the closed loop poles are going to be here. And the green is just describing how it's moving as you increase the gain k. So this gain equals 100, and they move across. And you can see this is a problem because in this scenario, right now, these two poles have crossed the j omega axis. So this is an unstable system. So as you increase the gain, so in this case, we're saying k GCG. Okay, so in our box diagram, we'll have a k, it'll pass through our GC, it'll pass through our system G. Okay, and it's got the classic sort of closed loop look to it. As you increase this gain, it might make the system unstable or vice versa. So that's why drawing the root locus really helps us because we can decide, okay, what's the maximum gains we can have? Because as we learned from before, usually by increasing the gain, we can make our system faster. It can, change the settling time, etc. So usually we like to increase the gain, but this tells us, at one point, things will start to go to become unstable. And the reason they're becoming unstable, so we talked about this -1 point, but why not, what about -2 or -3? And the reason why it's not just on the contour, like anything in the right-hand path or, outside that circle is unstable, is because instead of having negative feedback, you have positive feedback. Okay, so something with a negative feedback will slowly, I always draw a spiral, it always sort of spirals down into 0. Okay, and something with positive feedback, no matter what input you start off with, as long as it's non-zero, any sort of little input, it'll spiral and become unstable. So that's positive feedback, there's negative there. Okay, so, but that -1 point is our cutoff, okay? So that's the point, that's why we always make these equations equal. Okay, so you'll cover this during this week. I won't reteach it to you, but just if you come back and look at these slides, etc., this recording, hope it's recording, at the end, because they're going to throw heaps of rules at you, but a lot of them are quite simple, like it's always sort of reflected on the x-axis, etc., or things travel from, if there's things travel from poles to zeros. Okay. But the two main rules that I always just remember is that, so the root locus is on the real axis, left of odd number. Okay, so if there's an odd number of poles or zeros, it will exist. So you can see at this point here, so if we're working from the, we'll work from right to left. So if we look first at this point, okay, so we can see that there's one pole, okay, so it exists, and that green continues until we hit the first 0. Okay, then it stops because then, we're past the number of pole or 0. Okay, and then when there's the two poles run in front of each other, that increases the count to 4, so it doesn't do anything. But as soon as we get to this last pole on the left-hand side here, the count goes to 5. So then this green arrow exists all the way off to infinity. And something to note for later courses is that an asymptote, or it's relevant for this course too, but there's a little addition. So the second point is that so asymptote k equals n minus m. Okay, and I don't know why they call them n minus n. That's probably really bad to remember. So you might want to make this into, whatever you want it to be, but n is the number of poles and m is the number of zeros. Okay.
Hey Tim, I had a
And-
question.
Yeah, great. Jump in.
So can you see in the diagram where you've drawn the poles over there, all the X's and stuff? I was just wondering, like, what are the poles? Like, what poles are they? I'm not sure.
Yeah. So what the black poles are, and so anything in black, what we call, so those are the open loop poles and zeros. Okay, so with no feedback, so that's usually that's just, so you can see here we've got T, so T of S, okay, which is K GCG on 1 plus K GCG. Okay, so that's our closed loop transfer function. Our open loop transfer function, so I'll just call that GOL for open loop. That's going to be K GCG. Okay, we don't really worry about the K for now because K is just a gain factor, so that's constant. But the poles and zeros are going to be what the poles and zeros of our forward. We usually call it the forward path or the open loop transfer function. So coming back to this diagram up here, if we cut that feedback path and looking from input to output, so R to Y, we'd have KGCG. So effectively, so Root Locus, why it's so valuable is it can show us how the closed loop poles, what they will look like only given the open loop poles. So if we're given a plan, like let's say we're given a motor, we can measure it, look at the poles and zeros of its system using, I don't know, like bump tests or whatever you've been doing in your labs. And then you can use Root Locus to then predict how it's going to be affected when you close the loop, when you add some gain. And if you add, the reason I've said GCG is that we usually add a controller in here. So G of C, okay? And by modifying G of C, we can modify what the root locus is. Okay, by modifying the root locus, what we want essentially is to get those red arrows to be where these rainbow arrows are, rainbow crosses, okay? And that rainbow cross, coming back to pole placement, that rainbow cross is determined by the characteristic equation we want. So the poles and zeros, which are determined by, the damping ratio, which comes from the overshoot, the rise time, settling time. So there's that 3-step design I'd really love for you to remember, which is first we get the requirements, so overshoot, rise, settling time, and then we transfer that into our desired closed loop poles. So that'll be either written in zeta, omega n, or maybe phi d. And then from then, either we can make them equate to PID controller, so we can make them equal each other. But that only works in rare cases, because as you can see here, the only way for this to work is if we get those rainbow X's to lie on that green line, right? If they don't lie on the green line, there's no amount of gain we can do to change our closed loop poles so they can, be on that rainbow X. But what you're thinking right now is, okay, but then can't we change where the green line goes? And the answer is yes, we can change where that green line goes, and we can change it sort of in the inverse way, like of drawing our root locus, by changing where the open loop poles and zeros are. And as we've seen here, G of open loop is K GCG. So that GC we can change. And that's essentially just the whole control system course in a nutshell. Like if we have an elevator and we want it to rise to level 3 in a certain amount of time and with a certain amount of overshoot, how can we put a controller on it? How can we design it so A, it doesn't act unstably and shoot people through the roof, and B, it can meet some different, characteristics. Okay, does that answer your question?
Yeah. That's actually a really good explanation. I was just also wondering, as to what, you said the closed loop, the open loop poles are represented as the black squares, right? The black X.
It's the black X's, yeah.
And then you're trying to find
zeros.
and the zero, and then you're trying to find some sort of gain K that pushes it up into so that you can actually represent the closed loop system.
Yes. Perfect.
Okay.
Yeah.
Right. Okay. Yeah, I get it.
Yeah, so if K is 0, okay, so your closed loop system, no, if K is like 1, your closed loop system will just be, you know, somewhere on that green line. Okay, so by changing the gain, we can move those red up or down the green line wherever we want to. So that gives us 2 limits. So first, we don't want it to be unstable. And second is how can we shift them so they give us the ideal closed loop, okay? And so the second thing we want to look at, and I'll draw another diagram so it gets down here. You'll see this a lot later this week, okay? And it's similar to the S-plane I drew above, but essentially, if I give you, like, let's say I give you a settling time, TS, okay? And what I say is that it's going to be faster than some settling time. Okay, so that means we want on our S-plane, our closed loop poles to lie somewhere in that region. But let's say I also give you a damping ratio zeta. So I want it to be, you know, more damped than that line. Okay, that limits the region where our closed loop poles can be to this green region here. Okay, and let's say root locus, so coming back to our old system here, maybe say this is the x's. Okay, and let's say our root locus looks like this blue line. You'll understand why I draw it this way. But coming back to our first rule, so the root locus is on the axis left of an odd number of poles or zeros. So if we look, you know, this chunk here, we're not to the left of an odd number. And if we look at this chunk here, we're to the left of an even number. So no place on the real axis does it exist. And we know there's 2 asymptotes. And that's because the number of poles, so number of poles here is equal to 2, number of zeros is equal to 0. So that means there's 2 asymptotes. Okay, and there's just lines going up to infinity. And the angle of then is, and I'll write this under rule number 2. So theta A is just 180 degrees on n minus m. Okay, so in this case, it's 180 degrees on 2, which makes 90 degrees, which is why these blue arrows are at 90 degrees to each other. Coming back to this first example, we see that there's 4 poles and 1 0. So 4 minus 1 is 3, 180 on 3 means that's why we get these 3 green lines, and they're dividing 180 in equal thirds. Okay, and that's the angle that they go out from. So theta A is 180, and then we put in that odd number, so 2k plus 1, just to indicate that there's odd multiples. So in this case, we know, so coming back to the second example, if we look at the root locus, there's a certain amount of gains that we can have. Okay, there's a certain region of gain, K, that as we increase the K, the closed loop poles, which I'll draw in red, okay, they can travel up that blue line in that limited region. Okay, and that region will satisfy our damping requirements and our settling time requirements. And this is, as we look through some questions, you'll see this is a really common type of question they ask, giving you some requirements, and then you have to work out, okay, what is the region? And then you have to work out, okay, what is the gain that will get me poles, you know, in that certain area? Does that make more sense now? And did you have any follow-up questions on that note? These are really good too, by the way.
Yeah, no, that's a really good explanation. I get it.
Great. Does anyone else have anything that's sort of just not really making sense? Don't think it's just you. I'm sure everyone's thinking the same right now. So yeah, if you have any questions, feel free to turn your mic off, turn your mic on, sorry, and let me know. Okay, and while you're thinking, I'll just finish off this rule. So we know that the angle A is 180 on n minus m, but where are those asymptotes going to be centered? Okay, and that's why we call this phi A, which is the center of these asymptotes. So you can imagine these green lines all meeting at one point, or these blue lines meeting at this one point. Okay, and there's that point on the x-axis where those imaginary points meet is theta A, and that's just the weighted sum. So the sum of the poles minus the sum of the zeros, again on n minus m. Okay, and you can imagine that if you added up all the placements of all the poles and you subtracted them all the zeros and divided by whatever that number was, that gives you what we call this the centroid, I believe. I might be wrong on that one. But we call it the centroid. So that can shift. Okay, and as that shifts, the asymptote shifts. So, for example, we might have 3 asymptotes and they might be going 1, 2, 3. Okay, but we might want to shift it so it looks like this image here. So we could shift this whole thing back. Okay, and how do we do that shifting? Well, we change this balance. We change the number of poles and zeros. And how do we change the number of poles and zeros? It all comes GC, this controller. If we look at poles and zeros, and by doing that, we can change the root locus. And by changing the root locus, we can change where our closed loop ones are, which will give us our desired time responses. So I hope I don't sound like I'm harping on, but that's the key thing I'd love you to get out of this crash course is those steps, because those are the things as an engineer that you'll be asked to do. You'll be given a set of constraints. You'll be asked to use the maths of pole placement or PID design or lead lag compensators to then find, okay, what is the controller I want to put here to control this system? Okay, and you can also work, like usually we're working in vice versa. They give you a controller and they say, okay, what are the time characteristics? But usually in a design sense, you do the reverse. Did someone have a question there? Or?
Yeah, is the centroid always on the x-axis or can it be somewhere?
No, it's always on the x-axis, and a good way of explaining that is that the root locus is always mirrored. Okay, and the reason why it's always mirrored is because it's the same for positive frequencies as it is for negative frequencies. And that comes back to a lot of different things. Maybe one way of thinking about it is if you've ever done a Fourier transform. Okay, so if you've transformed a sinusoid, we get this arrow at the frequency, and there's also an arrow in this negative frequency mark, right? And you're like, oh, that's really weird. Why does that happen? It's because in the S-plane, we define a continuum of frequencies from positive infinity to negative infinity. But it's a really good point that you raise, and I'll just chuck this in here, but this is how Bode plots come to be. So what we do, I don't think you've learned about this yet, but I'll just pop it in here just in case you're going to be, I don't know, hopefully watching this recording at a later time. Add a Nyquist plot. So we know Nyquist is different to our normal, S-plane or Bode plots, because Nyquist is where this -1 circle has significance. And I'll just draw, usually you get something, they're really cool. They look like, hearts. I'll draw it in 2 colors. Okay, because they actually go from all frequencies, so omega equals infinity to omega equals 0. They cover all frequencies as they sort of wrap around that. And this comes back in terms of contours and residues, etc. But the main rule here is you don't want this, and I'll shade in green the area inside here. You don't want that to be to encapsulate this -1 point. And as soon as it does, either touch or encapsulate it, that's where we say the system is unstable. So no, don't worry if you're not, if you haven't caught up on lectures. But essentially, what we say is there's 2 main things, because we look at, okay, how much wiggle room do we have? So we look at first where this line crosses this -1 line, so that's this point here. And we know that, okay, well, if I just rotated this by a certain angle, I'd be hitting -1. So that's bad. So that angle there, phi, we call the phase margin. And we also see, okay, well, this point here in green on the x-axis, if I just shift that over a little bit, I'll be hitting -1 again. And that shift we call GM which is the gain margin. Okay, and these might seem a little bit arbitrary now, but when we look at a Bode plot, and that's the reason why for Bode plots, we only draw the positive frequencies, and it kind of makes sense, right? But all we're doing is we're unwrapping just half of that Nyquist plot, and we only need half because we only need half the frequencies. We know it's going to be mirrored. And let's say that's 0 dB here. And, you know, we've all seen a classic Bode plot, boom, boom. So that'd be one sort of pole. For every pole, it's like 20 dB per decade. I think this is sort of coming back from ELEC3114. Pretty sure we all got sick of covering Bode plots, etc. But it's cool here to see them coming in control systems. And don't be disheartened by all the stuff you're seeing in many courses, you know, behind you and ahead of you. You'll come across these same concepts just in different ways. And I hope it sort of ties in a bit together. We also have, so here is gain. I'll just draw them on 2 different axes, but we also have phase. Okay, and phase starts at, you know, 0 degrees, but also draw the 180-degree line. So at the point where the gain margin hits 0 dB, okay, so we know that 0 dB is equal to a gain of 1, okay? And we know that when the phase hits the negative 180 degrees, we know that's going to be negative. Okay, so at that point where we get to a gain of 1, if our phase line was this green, it was also going through negative 180, we know at that point exactly the total, so gain with angle phase, will be equal to -1, and that's really bad, that's unstable, etc. So then what we call that, I'll just erase this line. We call this here, again, this is what we call phi, which is equal to the phase margin. So we know that the phase can differ by that amount before becoming unstable. And the point where phi goes to hit 180, we call this amount here, which is the amount of gain between 0 dB and whatever the Bode plot is, we call that the gain margin. Okay, and the reason why we have these margins is because, you know, of course, as engineers, we design everything, we get, you know, the gain K is 3.426, etc. But when we're trying to implement those in, you know, op amps, resistors, tolerances, etc., nothing's going to be perfect. So we have these gain and phase margins just in case, okay? So just to allow for that wiggle room. So we know that, you know, our brand new fighter pilot jet plane isn't going to, you know, become unstable and crash out of the sky because, you know, 3.5 was rounded to 4 or something like that. Okay, so that was the little bit I wanted to add about frequency response. You'll cover this probably on the other end of this week, or maybe, you know, Arashman covered it all in the course. I think we were equally as behind at this point, but I thought it was important to cover just so you get a bit of exposure in it before we start looking at these, you know, root locus design and leader lag. Does anybody have any questions so far on that part that we covered? Even if it's new, you know, do you have any, I don't know, any things that you find that are interesting or you don't really get? Okay, cool. So coming back to this root locus, we know there was these 2 relations I was talking about earlier. Okay, and we have a name for them. So the first is what we call the Angle Criterion. And it says, so if a point, so we say the angle of GCG is equal to 180, and of course, you know, I'll put the little note on, that's usually 2k plus 1. Okay, we know that's on the root locus. But GCG, we know that's just going to be, you know, some numerator, 1 and 1 plus, you know, 4s plus 2 or something. You know, we've got to evaluate that for a specific s. So we draw this and we say s is equal to, and usually, you know, we evaluate these at, you know, the pole or the zero of interest. Okay, so usually we evaluate this at the pole, and that's our closed loop pole. Okay, so we substitute. So let's say we have, I'll write this up properly. Let's say we have GCG ends up being, 1 on S plus 1. Okay, and let's say we're given, zeta equals something, omega n. Oh no, we're not given that. We're given percent overshoot equals something, and the TS equals something else. We write that as in terms of zeta and omega n. That gives us our S closed loop. Let's say what that equals, I don't know, -4 or something like that. Okay, so we know that we want our closed loop S to be -4. Okay, so what we do then is we evaluate this GCG at -4, and if it's equal to 180, we know that it's on this root locus. Okay, and that root locus is defined by all the factors we were talking about before. Okay, and we don't really do that, right? Like we don't really do the guess and check. But what we do is by equating these two, because usually our GC has a bunch of parameters in it. It has, so GC for a PD, so differential gain is K S plus ZC. Okay, so that's some sort of zero. And for PI, so GC for PI, we can write that as K S plus ZC. Okay, divided by S, because we know PI has that that integrator element to it. Okay, so these two zeros are going to affect this root locus. Okay, so by making that equal, we can find where we want the gain of the differentiator or the integrator to be, such that our desired closed loop poles line the root locus. Okay. So the second thing we need to find out is, so this lies on the root locus, but we need to also use the gain criterion, which is K magnitude GCG equals 1 to find out, at what gain do we need? So at what gain do we need? So this red lines up to the black. So our closed loop pole lines up to our desired closed loop pole. Okay, and these are the two steps we use. So we can use them for PI controllers, and there's something also called lead lag controllers. Essentially, lead lag is combining a pole and a zero. So we have K S plus 0 on S plus pole. Okay, and that will introduce this pair of poles and zeros. Okay, and I won't go through. I will go through it a bit just in case anyone's watching a recording, but so you'll know when you go through the lecture on this, usually we start with a lead controller. Okay, and so our lead controller is very similar to our PD controller. And we know that our differential is usually focused on transient responses. Okay, so that means that we use the zero, as I was talking about before, with the centroid, the zero can shift our root locus wherever we want it to be. Okay, so it shifts these green lines, wherever they're going to be. We shift those green lines such that they lie on whatever our closed loop poles are. Okay, and then we choose the gain K to move those poles so they hit the desired spot. Okay, and for our lead, the main thing is because we add a pole and a zero, we want this pole usually to be much greater than whatever our other poles of the system are, just so it doesn't interfere. The main thing we're focused on is this zero. And for our lag controller, that's most similar to a PI controller. So our integral controller, and as we know before, our integral controller, what we want from that is by putting a pole at the zero, okay, we know that the error steady state goes to 0. But if we do a lead or lag compensator, you see that we can't, it's 1 on S plus P. Okay, so it's not just in here, this gain, it's 1 on S, here it's S plus P. So that pole will be slightly off 0. And that means our steady state error won't be exactly 0, but it'll be very close to that. Okay, so usually what we say is we have a -1 here, we have a 0 and a pole. We don't really care about the 0, so we make the 0, you know, at least 10 times. Usually we say much greater than the pole. And then you'll come across this when you go into your lecture, but for something like your error, so your KV, so your KV dash or your KV, you know, nu is equal to the ratio between the Z on the P. Okay, so that will affect, that ratio will affect your proportional error. Okay, so it can get bigger and bigger and bigger, but it can't be 0. And you might be asking yourself, you know, why do we use lead or lag if we can, you know, get zero steady state error if we just go with an integrator or differentiator? And the reasons for that, there's quite physical reasons. And you'll come across this if you ever try to implement some of these. So you'll notice in your lectures that sometimes they introduce these you know, filters in the design, etc. And that's because having a pole right on the origin is quite unstable, because if it shifts to the right even a tiny bit, you'll have an unstable response. And also sometimes physically, you know, you might need op amps to implement these systems. Okay, so that was just a little bit of a spiel on lead lag. Don't worry if it isn't sinking in yet. You'll have a lecture on this, but hopefully this is giving you a little bit of an introduction on why we add these poles and zeros, because we want to shift the root locus, because we want it to align to our desired closed loop poles. Okay, so I know that was new, but I really wanted to cover it. So do we have any questions on that section yet?
I believe you don't need active circuits for lead lag compensators, right? Like
Yes,
you can
yeah.
do without active circuits as well. Like we can do without op amp, I believe.
Yeah. So the active ones, those I was talking about for PI and PD.
Yep.
And you're correct. So the main reason we use lead and lag is that those can be simple RC or RLC circuits. And I think when you get onto in the lectures, I'm pretty sure it's like the last lecture, one of the last slides, he actually goes through some of the implementations of these, and it's really out of our minds, right? Because we're dealing with so much maths. But if you do later courses like design proficiency, or if you do further labs in control systems, you might look into actually designing some of these systems physically or in something like Simulink. And it becomes really important because we're trying to look up, okay, like lead lag is cool, but how do I actually make this on the breadboard? So that's where, yeah, lead lag controllers are really useful. So yeah, that was a really good point. Thanks for that. Okay, so that's a bit on lead lag design, root locus design. So the main things in terms of questions, hopefully we have time to go through a past paper, have a look through. But what you'll find out, you know, in your tutes is usually we use these two rules. So we use this angle criterion and then the gain criterion to find out, okay, what values do we need for KP, KI, KD, etc., or ZC or PC in case of the lead lag. Okay, but we're in the last half hour, so I thought we'd quickly switch on to a little bit of state feedback. I'm just going to briefly run over it, the concepts of it. You'll find that the maths is actually quite involved, and usually in terms of an exam, they give you a lot of formulas. So it's not, I don't know, it's not really useful trying to memorize a lot of these things, but it is useful to think about, okay, why are we doing these steps? And, you know, what's the process for finding out, you know, things like the gain, etc. So I'll start a new page and we'll look to state space. Okay, so Nicola, if you're there, any reason why we use state feedback? Like if all this closed loop transfer function stuff is so good, why has state feedback, you know, been a new introduction to the control system world?
Sorry, I haven't done much on state feedback.
Well, you will be in a couple of weeks, so I'm great we're going over this now. So state feedback essentially is it's looking at what is the state of your system. So if you have any sort of linear system, what we do is when we do the Laplace transform, okay, we're going from time into the frequency domain, so omega. What if we just stuck in the time domain and instead of making everything in terms of, S, what if we just, for something like an electrical circuit, what if we get it to the basic amount of state? So just looking at the voltage and the current, because if we, made those different parameters and we know how they worked, how they changed or evolved, by putting in any input, we can sort of know what the output would be. So for a state space, we look at the change in our state variable X, and we say that that's, a combination of two things. So first it's some sort of matrix A times whatever the current state is. So if you think about, a hockey ball that's just been hit, it's got a velocity to it. Okay, so that's going to affect the rate of change. But if we hit it with another hockey stick, there's also an input B, okay, and that just relates, it's just describing how they're related, which, relates it to the input U, okay? And then we look at the output Y, so Y can be whatever we want. It could be the speed of the hockey ball, it could be the position, etc. And that relation we describe as C, okay? And it's also of the current state, okay? And these sets of formulas we write, okay? And those are all we need to describe our system. Okay, so it's equivalent to writing, our G of S. And I'm sure you've gone through already, and I think we cover this a bit in the mid-sem, how to actually go between those two. I won't go through it today, but it's, mathematical, you can just sort of write them into each other. But essentially, there are two ways of thinking about the same system. So that system has some sort of input U, okay, which is usually some sort of negative feedback with input R, and then our output here is Y, and we have this state feedback vector negative K, which takes X, okay, so it takes our current state, and we provide negative feedback, and we compare, our current state with whatever our reference is to give our control signal to pass into the system again, okay? So coming back to pole placement, so if we have two closed loop poles, pole 1, pole 2, okay, we know that poles are related to eigen, I'm not sure if it's eigenvalues or vectors, I can't remember, but we know that's related to our characteristic equation. So pi of S is the determinant of SI. Usually it's minus, I think it's A minus BK. Okay, and that's just because in here we've got K, which is going to be multiplied with U, so it actually goes into that. That's why it's multiplied with B. I just thought I'd put that in there. I won't cover the maths as vigorously as your lecture slides, so I hope that's okay. But essentially what we do is we get this, so we've got our desired poles, so S squared plus, phi D, S, etc. And that's equal to, K1, like S squared plus K1 plus blah, 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 S plus, this is K2, blah, blah, blah. Okay, and these values of K1 and K2 will form this matrix K, etc. And that matrix will be what values are multiplied, whatever the current state is, to feed back into our system. So by looking at the current state, comparing to whatever the reference signal we want, we then can pass in control value U. So that's essentially how the state feedback law works. And the reason why we use it is that it can be scaled very, very large. So you can have a system with multiple states, which you can handle, rather than the Laplace transform way, where if you get above, a second order system, it becomes very messy really quickly. So there's two things we look at: controllability and observability. So Taban, do you have any idea what you think, controllability would mean, or observability, when it comes to these state space systems?
I think Okay, it's a far way down the control slide, but let me think about that. How to maybe because if the system is controllable or not. First of all, like I think that's pretty easy. And observability means I think if the system is observable, like
what are we observing? If you look at the system
of the output with the if you give an input and everything, we observe the output. What the output of the system is actually, basically.
Perfect. Okay, so if we give, so we can take our, what we can see is if we look at the system, we know what the input is, we know what U is. So let's say it's a motor. We know the motor, we know if we input electricity, we'll get out some speed. But we don't know what those state variables are. You know, maybe they're the flux going through the magnetic core, maybe it's the current in the wires. Okay, so we need to actually put sensors on those to get what this X value is. Okay, so to get what our X is, we need sensors to determine the states of our system. And remember, those states aren't unique. We just need at least so many states as to, you know, describe our whole system. And that comes back to this notion of linearity, which we also worked out in maths, because as you know from physics, a lot of these things are interrelated, right? Like the flux is related to the current. So sometimes that's why there's a minimum amount of, thanks, Andre. Thanks for that note. So that was just coming back to the complex poles for our system. But yeah, but those sensors are expensive. You know, sometimes we can't get into our motor. So first for controllability, as we said, what we want is to, given some initial condition X, can we find some U, so some controlling, you know, maybe it's a ramp or something, so we can get whatever from our input to X at a point time. Okay, so let's say after 10 seconds, we want our X to go from, you know, this point to that point. Okay, so it can do whatever it wants to get there, and we give it some sort of control signal U, okay, to get it there. And how do we do that? And we can check that there is some justification, but the main thing we'd be doing in an exam situation or just in life in general, we look at the controllability matrix. So that's B, A, B. So these are, you know, when you sort of put matrices alongside each other, and it keeps going dot 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 A n minus 1B. Okay, so depending on the rank, like how many columns your A has, will be the amount of multiplications you'll have. And what we want that, so that'll give us this big, you know, a big old matrix, and we want that to be full rank. Okay, because if it has a blank, you know, a zero vector, a zero column or row, we know that the determinant is going to be equal to 0. So we want it to be full rank. And the equivalent state of that is saying the determinant doesn't equal to 0. Okay, so we can either use Gaussian elimination to look at the full rank, or if it's a 2x2 matrix, it's quite fast to work out the determinant. Okay, and observability is on a similar scale. So essentially what we say is if we have this input R, it's coming in, we get U, which goes into our sort of state space, and we get Y. What happens if we measure our U, we measure our Y, we put them into some system, and we call that L, which is what we call our observer. Okay, and that L gives us this X with a hat. Okay, and that's what is our estimated. Okay, so it's our estimated state. So it's not our exact state, but it's something close to it. And then we pass that estimated state back through our K, you know, back as normal. And this is a control system as well, right? Because there's an estimation error, and we want that estimation error to somehow go to 0 over a certain time. So this whole, and you'll see I've just written L here, but this whole system is another control system. Okay, so we want that control system to be controllable, which is equivalent to saying this is observable, which is, we write this observability matrix, which is C, because it's related to our output, and it's going in the vertical direction now. I think it's like CA, CA, and -1, etc. Okay, and if that is full rank or the determinant doesn't equal 0, we can find that out. Okay, so essentially, but this is how the system works. And what we do is we can look into this second control system, and that's how we find the values for L. Okay, so L will be just some other matrix, and it will take in U and Y, and it'll spit out the value, the estimated value for X. And because it's a control system, we know, given some time, that error should go to 0. Okay, so that should be it for state feedback. One last thing you'll cover, it's a tiny thing. You probably won't get to ask a question on it, but this is important if you want to do future control system courses, is optimal control. Okay, so we say J, that's what we call our cost, okay? And we do maths to minimize that cost. So we say from 0 to infinity, which is time. We have Q, which is just a matrix times X, and we have R, which is times U. And what these two things do is they are what we call weighting. Okay, so they add weight to these values as they change through time. Okay, and essentially what we're balancing is two things. So first we look at the performance. So we look at this X here. Okay, so if we make Q very large, as X changes, our cost function J will change a lot. Okay, so our cost function will be very related to our performance X. Or we could look at U, and U is what we call the control cost, because that is the input signal. And we don't ever think about it, but in an electrical system, if we're inputting a very large control signal, that will actually be in terms of power. So we might be inputting a very large current or voltage, which will give a very large control cost. So by changing these values of Q and R, and by doing this integral over all time, we can pass it through a mathematical function to find the minimum cost, so the best values for X and U that still satisfy all our control systems, but just in reference to that cost. Okay, so that probably won't be covered. You might get asked a sort of explaining question like I've just done to you then. But especially if you want to pursue further control courses, that is really important. Okay, and that takes us, I think, to the end of all the theory. So a bit of an overview before we use the last bit of time to dive into some questions. So the first thing we've gone through is we've looked at PID control, okay, how they affect the transient response. So we're going to get given something like overshoot, settling time, steady state error. Okay, and then we think, okay, what are the optimum closed loop poles? So we get our desired closed loop poles, and then we look through a couple of different systems. So the first thing we can do is we can look at root locus and changing the root locus by using either angle criterion or gain criterion to add, extra poles or zeros. And that we can do via, PD, PI, or either lead or lag control systems. Well, the second thing we can do is using this in the state space, using this value K to change we change our eigenvalues or vectors. So we change our characteristic equation so the poles and zeros match. And that means that we can actually get the desired closed loop response. And that's the essence of a control system course. And then the job for us to do is just find what values of K or what values of KP, KI in terms of, PID controllers do we need to use? And then the extra things we look at is, okay, if we can't measure X, how can we observe it? And also, once we've got our control system, how can we look at how stable it is? So looking at, Bode plots or Nyquist plots to determine the stability margins. But if you look at this big page, I know, it's taken us probably 2 hours to go through this, but it's actually, it's not too much. Like there's a lot of details, but when you put it together like that, we are doing the same sort of things, just in slightly different ways. Okay, so while I put up some past exams, does anyone have any questions so far? Just on that last bit on state space.
Well, let's say, can a system be controllable but not observable, like,
100%,
or vice versa?
Yeah.
Is that possible?
So, yeah. So usually, yeah. So, what would be an example? So, yeah. So let's say we have a motor. Maybe there's a motor where if you measure the input current to the terminals and you measure the speed, maybe you'll never find out the internal temperature. Maybe that's something you can never work out, okay? But you can still control the motor, like you can still make some sort of feedback law. But yeah, definitely, I'm pretty sure those things aren't mutually exclusive. But yeah, double check on that one. Like I'm not, that would just be what I think. It's definitely probably not a fact, but I'm pretty sure in the lecture notes, which are Bible, yeah, they're mutually exclusive things.
Okay, sure. Thank you.
Okay, and usually if it's not uncontrollable, we don't really deal with it. But if it's observable, then we go through we create that observer, but it has to be observable first for us to do it. And the same as with controllable, that's why we do these checks, because it's quite simple to check if it's a full rank matrix. And that means we don't have to go to all the effort of designing a controller or designing an observer if we know that it's, non-observable and non-controllable.
Sure.
So because we only have 10 minutes left, what I'm going to do, I'm just going to I'm going to share my screen actually, because hopefully you'll be able to go through these questions in your own time. I'll share them. I'll put up a feedback form, I think sometime later, and there'll be a link to a Google Drive. You can go in and access these and hopefully just work through some final questions. So let's just join. But if anyone has any questions so far of what we've gone in, or any exam advice or studying advice, feel free to ask that now. Okay, and we can see my screen. Okay, so at the moment, so we'll go through 2015. So 2015, question 1. What it's going through, so it looks at stability, looks like a closed loop. Great. So look at the solutions here. So this will make more sense once you've done your feedback control. But you can see here, what I've done is we start with the conditions, okay? So they give us a condition on Z, right? Okay, and from that, put in the table the zeros on it. And then so what we want is, in here we're using the criteria GC at the closed loop pole equal, and then all you have to do, and then from there you find that Z or the value of that is 2.468. And then what you do is you sub that 0 back into the same equation and you find K. So in this case, our K is 44.843. So it means by adding that 0, we've shaped our root locus, which is this image on the left. And by doing that and giving that proper K, we can actually find these closed loop poles. Okay, Nicola, you still here? Does that make sense?
Yep.
Great. So question 2 was a rotational mechanism. So So here we are on question 2. I've told you guys a lie. So question 1 and question 4 are the same type of question, I'm pretty sure. Yeah, okay. Anyway, if you're watching the recording, please ignore that last little bit. I was at the wrong page. So question 2 here. What we're given is we're given a rotational mechanical system. So hopefully from the midterm, we know how to convert them, doing our Laplace transforms into our S. And then what it goes through is it looks through the state variables. And then also from the midterm, we had to look at the state transition matrix. We calculated the state transmission matrix. And then it says compute the step response. So it gives us dominant closed loop poles at S equals, I think, -3 plus or minus 4J. Okay, so you sub that into your desired characteristic equation. So you get S cubed, 14S squared, 95S. Okay, and then from there, what you can do is you can solve then for A minus BK. So this is solving here, you get the determinant, you work all the way through the maths until you get this S cubed plus S squared 1 minus K2 on 20. So you equate S squared to what the S squared in your desired closed loop was. So that'll give you 14. And that leaves you with K2 equal to 0.650. Okay, and you do the same with K1 and the same with, KE, so that an integrated gain. And that gives you this I'm not sure if I didn't draw a box diagram, but that gives you that state feedback law K. It gives you that matrix. Okay, so essentially we find the desired closed loop poles, we worked out the maths in terms of the determinant, got to our characteristic equation and then solved for that. Okay, question 3, we looked at a transfer function. So it says determine the part of the root locus. So again, during this week's lecture, you'll go through the root locus. You can see through here, I calculated the centroid, which is at -5.4, and the angle, which was 90 degrees. Then it seems I did these out of order. Then part F gave us, damping ratio of 0.6 and a peak time of pi on 4. So again, we went through that, got our value K. What else? And then it gives us, it says it's question 4. Question 4 gives us a Bode plot. It asks us to find the gain margin, phase margin, and essentially what we do is you draw it out, you have a look at where the gain crosses 0 dB, and I found that the phase at that point was 20 degrees above 180, so that was the phase margin, and I did the same thing for gain margin. Okay, and that was that paper. So remember that these 4 exams, they're actually, it's really bad. They're from before Arash taught. So if you've got access to Jaden, do you know if you have access to the 2019 paper?
I haven't seen it on Moodle yet, but we might be able to ask Arash to upload it.
Okay. Yeah, that would be really great because I remember when I did the exam, I don't have it with me, but I think it was quite similar, which is good, but it'd be good to have a look at that in terms of just the different styles of questions Arash would ask. So yeah, having a look at the tutorials, really just going through, practicing them again would probably be your best bet. Have a look at these past papers. They're good just because they're new, they're different. And you can see there's only 4 questions in these exams. So unlike tutorials, these questions are a lot more interconnected. They flow on from each other. And another good resource, if you haven't had access yet, is of course the textbook. If you compare Arash's notes, a lot of the examples he takes from the textbook. So, you can get an online copy through the library, or if you're on campus, pick that up. I found that really helpful as well. But we'll just cover the last 3 exams so far. So question 1, very similar to last question, a rotational system. You'll get, a rotational or some sort of spring balance. Sometimes you can get an electrical. We'll cover that a bit. So we'll find the transfer function from there. And then it talked about critically damped, overdamped, underdamped. We know those are just, I've drawn this image here, which is how the poles are related on the S-plane. Then what it says, there's error, steady state. Okay, in part E, yeah, so it says it sets the gain to 256, and then it says for us to find the rise time, percent overshoot, peak time, etc. So what you can do is then just substitute the gain in, you get your closed loop poles, so S1 and 2, and then from there you can find your omega n, rise time, full time. Does that make sense, Andre?
Yep.
Yeah, cool. And then yeah, goes to a ramp, great. Question two is something I've written on the paper. It's not something we really cover, block diagram reduction. Yeah, essentially this is a lot of maths. There's a Rath-Hurwitz test. Yeah, no, it's not really one. Question 3 is a classic sort of root locus. So again, determine the part of the root locus on the real axis. What we do is we look at the open loop transfer function, G of S. We draw those poles and zeros. So we can see that there's a 0 at S equals -4, a pole at 0, and a double pole at -1. So that is our open loop poles and zeros. And then from there, we can draw the closed loop. So our root locus on there by drawing, the centroid, the angle, etc. Part C and D, no. Okay, part F, we say we put it in a unity feedback controller with some controller, PID, and then we want to achieve some sort of gain margin and phase margin. So essentially, you can just write out that equation there, and then work out what our phase margin and gain margins are, and you can then from there get your gains, K, etc. Cool. And question 4 was another bow plot. So you can see they all follow, these ones follow very similar. Maybe Arash makes different ones, but at the start, there's some sort of Laplacian question, usually maybe a steady state error or, rise time, etc. And then usually there's a big question on root locus and pole 0 placement to get those desired closed loop poles. And then they might finish with maybe a frequency response question. So there's 4 past papers here, really good to work through. They're probably 2 hours each, to work through. So I'd really encourage you giving those a go. I'll put them on a Google Doc for you. But we've hit our 5 o'clock now. So does anybody have any closing questions or comments before we leave? No, okay. Great. So I know we went really high level this time, and I hope that's given you a bit of an overview of what we've covered so far during the course. So, and those key components of control system design that we covered so far during the term. And those steps, I hope, will guide you in your final exam and in working out, okay, what steps do I need to do? And now it's up to you to go through those tutorials, go through those past exams to get a bit of experience, I guess, with answering those types of questions. But yeah, I hope this overview has sort of helped you get an idea of, what things you know and what things you may need to look into a little bit. And again, so I'll put up a feedback form sometime tonight. I'll post it on. And then from that, there'll be a link to a Google form if you want to get those past exams. But other than that, thanks for joining. Anyone on the lecture recording, thanks for joining as well. I hope this has helped, and yeah, good luck on your final exams.
Thanks.
Thank you.
Okay, bye-bye, everyone.
Thank you. Thank you.